Hello and welcome to the keynote session to be given by Professor De Luca. I have the privilege today to introduce the speaker. Occasionally in life, things that make you happy professionally coincide with things that make you happy personally, and this is one of those events for me. I'm happy to introduce to you Professor De Luca, who is now a professor of robotics in the Department of Computer Control and Management Engineering at La Sapienza in Rome. I learned La Sapienza means the wisdom. So he'll be bringing the wisdom today. He's had a long and distinguished history of interacting with and doing things for and being a leader in the Robotics and Automation Society. He has a long CV, and I'll summarize some of what I think to be the highlights as an introduction. He has been the editor-in-chief of the Transactions on Robotics, presided over some of the glory years of that transactions, including the grand split between the Transactions on Robotics and Automation into two separate transactions. He ushered in the Transactions and Robotics. He's been the general chair of ICRA in 2007. He'll be the program co-chair for ICRA in 2016 next year in Stockholm. He is an IEEE fellow. He's won the Distinguished Service Award that our society gives a few years ago. That's all nice stuff, but of course what we care about, the reason that one comes to a plenary session, is because of his technical contributions and credentials. He's won the Humboldt Research Award in 2005. He's won Best Paper Awards at the conferences that you care about, including ICRA, IROS, and BioRobe. And this year, one of his papers for which he's a co-author is a finalist. And the paper that was a finalist for the Best Paper Award this year is related to the talk that he'll give today. His research interests include human-robot interaction, dynamic modeling and control of robots with flexible elements, visual servo, nonlinear control of manipulators and wheeled robots. That is much of it related to the project that he currently leads in the FP7 program called Safari, Safe and Autonomous Physical Human-Aware Robot Interaction. He's the coordinator for that. Please join me to welcome Professor Alessandro De Luca.
Thank you, Seth. And welcome to this keynote. I'm very honored to be having been asked by the organizer to talk about the research that myself and my group and other colleagues in a European project are conducting since a few years. So Control of Architecture for Human-Robot Collaboration is a title which tries to cover the many aspects that have been developed lately. So let's say the domain of interest is human-friendly robotics. So we want to move away from traditional robotics. This is that used to replace human with robots, to the situation where humans and robots will collaborate. And this is going to happen, and it's happening already now, both in industrial settings, so we talk about co-workers, and in homes or in other service robotics application, both professional and entertainment. So this is the context, and in particular, we are interested in the physical aspect of this human-robot interaction. Of course, the cognitive aspect is as important, maybe even more, but without the physical aspect, you will see that you don't go farther. So my background is in robot control, so I present here a few control problems which are safety-related and which are important in human-robot interaction. In particular, the handling of contact, which may be harmful, so they become collision, and how do you detect collision, and how you isolate this collision, and what the robot should do in reaction to that. And possibly I will present some solution that do not require any external sensing. They just can be implemented based on the robot's own perceptive sensing. Of course, this is kind of the last event when a collision occurs, so you would like to have collision avoidance continuously, permanently, whatever the robot is doing, and this will allow the task to run despite the fact that the human entered the workspace. There is another situation which is relevant namely when this collision becomes intentional contact because human and robot would like to collaborate. So instead of escaping possible contact, you have to the robot should look for contact with the human, understanding which parts should go into contact and how you handle this interaction at the physical level. And possibly, since this contact may occur at any place along the structure of the robot, like in whole arm or manipulation, then you would like to rely not on specific sensor like tactile sensor or proximity sensor or force torque sensor, if possible. So in this respect, these basic problems correspond to 3 layers of control architecture that we have been developing over the last 3-4 years. The lowest layer is safety. Safety in the sense of physical contact, so detecting collision and reacting to collision. Of course, this includes also mechanical redesign of the robot, which should be compliant, possibly at the joints, maybe with soft coverage, lightweight links, and all this mechanical part. From the control point of view, you build upon this mechanical and electronic advancement to design a safe strategy. And this is the lowest layer of our architecture. Coexistence, we call coexistence the fact that the human and the robot are sharing their workspace. So, of course, this is the most interesting part right now, but you don't have to forget about safety, because a coexistence without safety makes no sense. So safety is always present. On top of that, like in a subsumption architecture, you have these coexistence capabilities that you have to guarantee. Finally, collaboration. So this is the highest level of this hierarchical control structure. You can collaborate in several ways. Of course, we are interested in the collaboration which is physical, not contactless. Of course, you can exchange information with the robot by voice, by gesture, and so on, but even pushing in selected places the robot to let him change operation or task. And again, collaboration is important, but collaboration should coexist with the fact that other parts of the robot do not collide with the human, except for the selected arm or a hand or whatever part of the human body. And if everything fails, the safety layer is also always there. So in this sense, I will present some solution for each of these layers and some examples through videos that shows how they coordinate and what they represent in terms of robot behavior. So suppose that we want to do collision handling. So we start with planning a motion to prevent, of course, this collision. Then we execute the motion and we use our feedback to control and avoid in real time online collision. But if something fails, if the human is too fast for the robot or some unexpected motion occurs, you may collide, and so you want to detect collision. And you have to distinguish if this is intentional or not. And in case, you have to react or replan the structure. So the following slide concerns this aspect. And for the collision event, we developed after a few years a pipeline which goes from detecting a collision, so saying yes or no, there is a collision or contact, isolating a collision, which means locating the link where the collision has occurred and possibly also the position of this contact point. Identification means reconstructing the joint torque, which is caused by this collision, and eventually also the Cartesian force in this contact. This terminology comes from the literature on fault diagnosis, so it's fault detection, isolation, identification, and in fact, our solution sees a collision like a fault occurring to our system. And then you can also classify which type of contact has been. It's accidental, intentional, if it's severe. Of course, this metrology of collision is very important. And finally, react to as fast as possible and in the most intelligent way. The simplest reaction you can think of is to stop the robot. And in fact, in